Okay, so today we're going to start Unit 11, which is called Solution, and Section 1 is called Water, the Universal Solvent, Solution, and Concentration. Okay, so this unit we're going to talk about solutions. Remember that solutions were two or more compounds mixed together. Okay, so the definition for a solution is a liquid that is completely homogeneous mixture of two or more substances. Remember from before, homogeneous was a mixture. Mixtures can be physically separated. And homogeneous was that if you look at it, it looks the same throughout. Okay, so heterogeneous was that you would see the different layers. Homogeneous was that you would not see the different layers. So a solution is a liquid that is completely homogeneous mixture of two or more substances. Talking about solutions, we have two new vocabulary. One is called the solvent. So solvent is the dissolving agent. Solvent is what we're going to be dissolving to make a solution. So what we're going to be using to dissolve the solute. Okay, the solute is a substance that is being dissolved. So for example, if we have water and salt, water will be the solvent because water is what's dissolving. Salt will be the solute because solute is what's being dissolved. Water is a universal solvent. So 90% of the time, water is going to be used as the solvent, as a dissolving agent. But it does not always have to be water, okay? Solute is whatever we're dissolving into our solvent. If we mix sugar and water, sugar will be the solute, water will be the solvent. Okay, so let's pretend that we have a glass of water, right? And this is my NaCl. I have NaCl here, which NaCl, sodium chloride, is table salt. And I shake it, and I sprinkle some salt on my water. Okay, so what's going to happen to that salt as it hits the water? Well, what's going to happen is that the salt is going to dissolve, okay? And if we take a closer look, like let's say we get a little microscope and we look here and we zoom it out, we're going to see that sodium chloride is going to dissociate, okay? It's going to break apart. It's going to dissolve into the water. And what's going to happen in a molecular level is that, remember that NaCl, sodium being the metal, has a positive charge. It becomes a cation. Chlorine, being the non-metal, gains electrons, becomes negative, the anion. Okay, so what's going to happen is that water, since water, H2O, okay, water is polar. That means that oxygen is more electronegative, pulling the electrons closer to its nucleus, giving it a partially negative sign. Hydrogen becomes partially positive, okay, because of this negative side and positive side of water. That's why water is polar. So what's going to happen is that this positive sodium is going to be surrounded by the negative side of water, which is the oxygens. Okay, so the oxygens are going to kind of surround the positive sodium, okay, and separate it from chlorine. Chlorine being negative, it's going to be surrounded by the positive part of water, the hydrogens, okay, because opposite attracts. And here, oops, well here, this wouldn't be here. Hydrogen, hydrogen, oxygen, hydrogen, hydrogen, oxygen. Okay, and this one, the oxygen will be close to sodium. Okay, so that's what's happening. If I were to evaporate this and remove all of this water, then the sodium and the chlorine will reconnect and make the solid again. But in this case, water, is it acting as a solute or the solvent? Okay, in this case, water is the solvent. Is the one dissolving the salt. Sodium chloride, NaCl, table salt, it is the solute. solute. It is what's getting dissolved. Okay, so solvent, it's what's doing the dissolving. Usually it's what we have more of. Okay, so in this glass of water, there's more water than salt. So water is a solvent. Whatever is being dissolved is a solute. So here I have a glass of water, and I'm gonna add some salt to it. If I add some salt to it, some sodium chloride, you see that my salt goes to the bottom, but then if I stir it, let me maybe take this one out so you see them better. You see the crystals in the bottom, but if I stir it, all my salt will dissolve. All my solute, my salt will dissolve in my solvent, the water. Okay, so my salt was able to dissolve. But you see that here I'm using a metal spoon. I put it in the water, and my spoon is not dissolving in the water. Right, so there's some factors that help you determine if something is going to be dissolved in water or not dissolved. And that is called solubility. Okay, so solubility is whether or not a solute, so whether or not my salt, my solute, or my spoon could be my solute, will dissolve in a solvent and the extent in which it will dissolve. So solubility, not everything is going to be soluble. Okay, not everything is going to be able to be dissolved in a solute, whether it's water, alcohol, acetone. Okay, there's many videos in YouTube of putting styrofoam in acetone. So you see that acetone dissolves the foam in that case. Okay, but solubility tells you if something is soluble or not. So my salt was soluble, but the spoon, this metal, is not soluble in my solvent, which in this case is water. There are some factors that affect the rate of the solution. So dissolution here is how fast something dissolves, okay? So there's going to be some factors that affect how fast something dissolves. One of it is increasing surface area of the solute. So you saw that when I added my salt to my water, the salt that I was adding was small crystals. So if I were to ground it into powder, I'm going to increase the rate of dissolution by increasing the surface area. Okay, I can increase how fast something dissolves. If I were to put a brick of salt in here, it would take a long time for it to dissolve. It can happen, it will happen, but it will take a long time. Just like if you get a lollipop and you put it in water, right? It's gonna take a long time, but if you get a lollipop, you crush it, you grind it, you increase the surface area, your lollipop will dissolve into the water faster. So increasing the surface area affects the rate of the solution, affects how fast something dissolves, if it's soluble. Another factor is stirring or shaking. This helps to disperse the solute particles and increase contact between solvent and solute. So you notice that when I put my salt here, I use my spoon to stir it around. If I did not stir it around, my salt will still dissolve in the water, but it would just take longer. Okay, let's actually do a little experimental while I talk. So I'm gonna pour a little bit more salt, and I'm not gonna stir it, I'm just gonna leave it there, and then I'm gonna show you guys later how it dissolved by itself. So let's just sprinkle a little bit. You see the crystals in the bottom. Okay, so I'm not gonna stir it, I'm just gonna place it aside. So you see the crystals there. I'm not gonna stir it, I'm just gonna place it aside and see if by itself it dissolves. So even though we don't see the water molecules moving, like even though the water is not moving, staying still, inside the molecules are in constant motion. So even if I don't stir it, it would stir itself around. So I'm just gonna leave it there and not shake it. And I'm gonna continue talking about the third factor that affects the rate of the solution. Okay, so increasing the temperature, if I increase the temperature of my solution, the collision between solvent molecules and solute are more frequent and of higher energy. So my water molecules are going to be moving around faster, impacting those salt particles and therefore dissolving it faster. This helps to disperse the solute molecules among the solvent molecules and speed up the dissolving process. So if I were to get this, which my salt crystals are still there, and if I were to heat it up, that giving this solution energy, by heating it up, it will cause my water molecules, my solvent molecules, the water, and the solute, the salt, they would increase the way they move, making my salt dissolve faster. Okay, there's a term that says like dissolves like, and this was in the Edpuzzle last week. And what this saying means is that polar substances, like for example, water is polar because remember, water, the oxygen pulls the electrons closer to its nucleus, making water molecule have a partially positive and a partially negative side. So polar molecules is going to be able to dissolve things that are like them, things that have a positive and a negative side. So like dissolves like. Polar molecules are going to be able to dissolve other polar molecules and ionic compounds, because remember, ionic compounds also have a positive and a negative side. Non-polar molecules are going to only be able to dissolve non-polar molecules. So non-polar molecules do not have a positive and negative side, so they can only dissolve other non-polar molecules. That is why water and oil do not mix. Okay, water is polar, oil is non-polar. They do not mix, so they cannot be dissolved in each other. They do not mix. Polar and non-polar do not mix because they don't have that positive negative attraction. So water and oil do not mix. That's why when you mix water and oil, you see a heterogeneous mixture. You see the line of oil and the line of water. They don't get together. Okay, if we take a look at our salt water that I have been leaving there without stirring, you could see that there's still a little couple of crystals left right here. But for the most part, all the other crystals are gone. Let me bring this closer. See this, a crystal right here, but for the most part, everything else has been dissolved and I haven't touched it. Okay, so even if I don't stir it, by stirring it, I increase the speed that it dissolves, but even if I don't stir it, it will still dissolve. So I'm gonna do another little demo, and I have my salt water here. My salt, like I said before, there's only one little crystal. Oh, actually, I don't think it's a crystal. I think that's just a glass in the bottom that's broken. So yeah, there's no crystals, they're all gone. But what I'm gonna do now, I'm gonna have my glass water and I'm gonna add some food coloring drops. And the reason that I'm doing this is because I'm gonna show you that I'm not going to stir my water. Okay, I'm gonna try not to move the desk too much. But by itself, you see how I added a drop of food coloring. By itself, this food coloring is going to be mixed through the whole solution without me stirring it. I'm gonna put it in another angle now. Okay, so after leaving this water here for a while, you see that the food coloring has been dissolved through the whole thing. So even though we didn't physically move it, you see how there's no spots that doesn't have food coloring? Even though we didn't physically move the water molecules are always in constant motion. So that's why, and you still see it there, the food coloring is moving on its own. Okay, so there's three different types of solution. The first solution that we're going to talk about is called a saturated solution. And this is a solution that contains the maximum quantity of solute that dissolves at that temperature. So a saturated solution, what that means is that it's going to be a solvent, like let's say water, that has dissolved the most amount of solute that it can. Okay, so visually, A saturated solution, it's going to be a container. It could be a beaker, a test tube, whatever, filled with my solvent. In this case, my solvent is those little blue squiggly lines. And visually, my saturated solution is going to have some crystals in the bottom, some undissolved solid in the bottom. That crystals in the bottom means that my solution is saturated. It has dissolved the most amount of solute that it can at that specific temperature. If I change the temperature, then that's going to change. But for that temperature that I'm in, if I have crystals in the bottom, I've stirred it and I've stirred it and I've stirred it, and those crystals do not dissolve, that means that my solution is saturated. It cannot dissolve anymore. Okay, it cannot dissolve any more solute. The next solution we're going to talk about is called an unsaturated solution. So here, this is a solution that contains less than the maximum amount of solute that can dissolve at a particular temperature. So an unsaturated solution, what that means is that it's going to be a solution that still has a capability of dissolving more solute. So visually, if we have a container, I make this container bigger, and it's full of solvent, okay, it's gonna have some solute dissolve in there. But if I add, this is my little salt shaker, if I add more, it's going to dissolve whatever add more, okay? It does not have any crystallization in the bottom. So visually, I don't see anything in the bottom. It looks clear. But if I add more crystals, I could dissolve more. Okay, so unsaturated means that I have less than the maximum amount. My solvent still has a capability of dissolving more. The last solution is called super saturated solution. So there's a solution that contains more solute than is possible to be dissolved. Okay, so visually, a super saturated solution looks the same as an unsaturated solution. Okay, so it's going to have my solvent, and it's going to have solute dissolve. A super saturated solution is not going to have any crystals or any solids in the bottom. Okay, so it's going to look the same as an unsaturated solution. Remember that a saturated solution is going to have some crystals in the bottom that cannot be dissolved. Unsaturated, it doesn't have any crystals in the bottom. But if I add more crystals, those crystals are going to be dissolved. A supersaturated solution, it looks the same as an unsaturated solution. There's no crystallization in the bottom. But if I were to add more crystals, okay, into my supersaturated solution, what's going to happen is that everything, since a supersaturated has more solute than possible, when another crystal is introduced to my solution, a bunch of crystallization is going to form, and now I'm going to have a lot of solid in the bottom. Now my super saturated solution is going to be turned into a saturated solution, okay? In where everything that couldn't be dissolved by the solvent came out and formed a solid. So there's a little bit of complicated, but I'll explain it more. So supersaturated solutions are very unstable. They're very unstable because either scratching the glass or introduction of a crystal can crystallize everything that was not supposed to be there. Okay, so the way you do a supersaturated solution is that you get your solvent. Okay, let's say we're doing salt water. You get water and you add salt until you have achieved a saturated solution. Okay, so once you have achieved a saturated solution, and you know that you've achieved a saturated solution because you've added salt, you stirred and stirred and stirred and stirred and stirred it, you wait some time and nothing happens. I still have crystals, undissolved crystals in the bottom. That means that I have a saturated solution. Okay, now I get this saturated solution and I heat it up. Okay, I heat it up, so I warm the solvent so that it will dissolve more, and then I cool it down. So I heat it up, I make sure that all my solute has been dissolved, and then I cool it down very slowly. And now I have made a super saturated solution. So I took a saturated solution where it couldn't dissolve anymore. I heated it up, I forced it to dissolve all my solute. And now I have a super saturated solution. I could either warm it up or I could evaporate some of the solvent carefully so the solute does not solidify and come out of solution. So I could either warm everything up, or I could heat it up enough that my solvent dissolves. My water dissolves, leaving more salt to less water ratio. Okay, but a supersaturated solution visually looks just like an unsaturated solution. But the test is by adding a crystal. Okay, so if I add a crystal, if I add a crystal of my solute, if everything recrystallizes, then that means that I had a supersaturated solution. If the crystal just dissolves, that means that I had an unsaturated solution. Okay, but by testing if I had a supersaturated solution or not, I now turn it into a saturated solution. Okay, so by adding the crystal and making everything crystallize in the bottom, now this, since it has all these crystals in the bottom, it is no longer super saturated. It is now just saturated. So here I have three containers. These little purple spheres, are crystals in the bottom. Okay, so by visual inspection, if I ask you guys to tell me what beaker is saturated, super saturated, or unsaturated, so you would say, okay, this one has some crystals in the bottom, so that one is saturated. Okay, because visually I know that this solvent cannot dissolve any more solute because I have some solute left over in the bottom. So this one is saturated. Now this two, they don't have any crystals in the bottom. So one is going to be unsaturated, one is going to be super saturated. It doesn't matter which one I do. I don't know yet. So visually, one is super saturated, one is unsaturated, and that will be correct. Okay, so that's correct. Now, to test if I am correct or wrong, what I would do is I would add a crystal to my unsaturated solution. If I add a crystal and it dissolves, then that means that I was right. This was an unsaturated solution. More solute can be dissolved here. Now, if I were to add a crystal to my super saturated solution, if I were to add a crystal, okay, and what happens is that more crystals are formed, so this one goes to the bottom, and more crystals are formed, then that means that yes, I was correct. This was a super saturated solution. So it used to be a super saturated solution, right? More crystals form, but now it is not super saturated anymore because now I have crystals in the bottom. Now it's just a saturated solution, okay? Because now I have crystals left in the bottom. That means that my solvent, my water or whatever liquid I use to dissolve this solid has dissolved the maximum amount of solute that it can. Okay, so regardless of what type of solutions you have, whether it's saturated, unsaturated, or super saturated, another important part that you always have to know is the concentration. Okay, and this is a measure of the amount of solute that is dissolved in a given quantity of solvent. Concentration basically is how concentrated or how much solute is dissolved in your solvent. So if we're talking about salt water, is how much salt is dissolved in your water, right? You could have a very salty salt water or a salt water that's not as salty. So concentration tells you how much solute you have dissolved in your solvent. So you could have a diluted solution. So this, if we're talking about salt water, this would be like a very weak or not as salty salt water. A diluted solution is a solution that contains a relatively small amount of solute. So this would be like, or if you're making Kool-Aid, a Kool-Aid that's kind of like watered down. There's not that much Kool-Aid powder in the solution that you've mixed in the water. So you have diluted solution and you also have concentrated solution. So a concentrated solution is a solution that contains large amount of solute. So this would be like a very salty water, or if you're making Kool-Aid, a very strong, sweet, potent Kool-Aid solution. So concentrated solution is that you have a lot of solute mixed in your with your solvent. Diluted means that you have diluted it down a lot, so it's not as strong. It has a small amount of solute. The way we measure this concentration of any solution, whether it's a diluted or a concentrated solution, the way we measure its concentration is by using something called molarity. Molarity. And we use a big M for molarity. Remember that little M O L stands for mole. Okay, so here big M stands for molarity, and molarity is the amount of moles of solute dissolved in 1 liter of solution. So molarity is how many moles. Remember that moles tells us how much the moles of solute, so how much solute has been dissolved in liters of solution. So here the unit for how much solution we have is going to be liters. Okay, because remember we could use a graduated cylinder to measure liters or milliliters and then convert it into liters. And we could use a scale to measure grams and then go from grams to moles using the molar mass. Okay, so molarity is known as the molar concentration. So whenever you see this word molar concentration, you know that we're talking about molarity. So the formula for molarity is molarity equals moles of solute. So how much solute have you put divided by liters of solution. Okay, so in the example that I previously showed you, my solution was the final thing, right? The salt plus the water. Solute will be how much salt did I add. So if I was in a lab, what I would do is I would get a scale, measure how many grams, using a scale, how many grams of salt I put in my solution. Then using math, I would divide how many grams of salt I put divided by the molar mass of salt to get the moles. Then get the amount of moles divided by the liters of the whole solution. So I would get the salt plus the salt water, put it in a graduated cylinder, and see how many liters I have. Okay, so the formula for molarity, remember molarity was big M, is moles over liters. Mole over liter. Moles of solute divided by liters of solution. And this tells you its concentration or its molarity. Okay, molarity, it's the same thing as its concentration. Okay, so let's do an example. It says a saline solution, remember the saline solution, that is a salt water solution, contains 0.90 grams of sodium chloride in exactly 100 milliliter of solution. What is the molarity of the solution? So they're asking for molarity. Remember that molarity is big M, and that equals moles of solute divided by liters of solution. So we need to know the moles and we need to know the liters. Okay, the first piece of information that's given to us is how many grams of solute was given to us. Remember, solute will be the salt, what's being dissolved. So we have 90 grams or 0.90 grams of NaCl. The first thing we need to do is we need to turn these grams into moles so that we can plug it into the molarity formula. And the way we do this is by doing stoichiometry. Okay, so the first thing we need to do is we need to go from grams to moles, and remember that we do that by using the molar mass. Okay, so we need to find the molar mass of NaCl. Sodium has a mass of 22.99. Chlorine has a mass of 35.45. You add them both, you get 58.44 grams per mole. You divide by the number, grams of NaCl for every 1 mole of NaCl. And remember, the reason that we want this is so grams cancel out. We're left in moles. And we're going to have 0.0154 moles of NaCl. Okay, so that's the first piece of information that we needed, moles, so we could plug it into here. Now in the bottom, we see that the liters, the units, is liters. The information is giving us 100 milliliters. So my second step, so here I went from grams to mole, right? In order to get the moles, to put it in top of the equation. In the bottom, I need liters. So now what I'm going to do is I'm going to go from milliliters to liters. And we did this at the beginning of the year. So I'm going to start with what was given to me, 100 milliliters. Okay, and I'm going to use the Kin Henry died upstairs drinking chocolate milk. For milliliters to liters, you have to make 3 jumps. Or I also can remember that in 1 liter, there are 1,000 milliliters. So I'm going to divide 100 divided by 1,000 so that milli goes away and I'm left in liters. So if I divide 100 divided by 1,000, I get 0.1 liter. Okay, so now I have the correct units. I have moles and I have liters. Now what I'm going to do is I'm going to plug in both of these numbers into my molarity equation, which I'm just going to recopy it here. So molarity equals moles over liters. Moles, I just calculated it. I have 0.0154 moles of NaCl for every 0.1 liter. Okay, so I'm going to divide 0.0154 divided by 0.1, and I get 0.15 big M of NaCl. And that is my molarity. That is how concentrated I have. So that means that I have 0.15 moles of NaCl for every 1 liter of solution. Okay, so for every, if I were to have 1 liter of this NaCl solution, I would have 0.15 moles in that 1 liter. So example 2 says a household laundry bleach is a diluted aqueous solution of sodium hypochlorite, which is NaClO. How many moles of solute are present in 1.5 liters of 0.70 molar NaClO? Okay, so now this question, they are giving us the liters. They are giving us the molarity, and what they're asking us for is how many moles of solute. Okay, how many moles of solute? So, big M, molarity. Okay, every time you see this big M, capital M, you have to think of molarity. And molarity is moles over liters. Moles of solute divided by liters of solution. So they are giving us the molarity, 0.70. They're giving us the liters, 1.5. And what they're asking us for is for moles. Okay, so the first thing I'm going to do is I'm going to plug everything in because my volume, my liter is already in liters, and big M is already in big M. Okay, so I'm going to plug everything in. So big M molarity is 0.70. And instead of a big M, I'm going to put mole over liter. Okay, remember that molarity equals moles over liters. Mole over liter. Excuse me. Equals moles. That's what I'm trying to figure out. So I'm going to put X for mole. And then liter is 1.5. Okay, so I'm going to work this out a little bit different than I've worked out in the past. I'm going to actually show you. So the first thing I'm going to do is I want to isolate this X, right? And this X right now is being divided by 1.5. So to get rid of this number in the bottom, what I'm going to do is I'm going to multiply both sides by 1.5 liters. Multiply by 1.5 liter. Here, this 1.5 and 1.5 get canceled out. So I'm left with X equal 1.5 liter times 0.70 moles over liters. Okay, so I'm going to multiply 1.5 times 0.70. But if I look at my units, I'm going to notice that the liters cancel each other out. And it makes sense that moles is the only unit left uncrossed because I'm looking for moles. So now I'm going to multiply 1.5 times 0.70 and get 1.05 moles, because moles is the only unit left uncrossed. And we're talking about NaClO. And that is my final answer. Okay, I didn't really have to do it right down this step. I could have just seen it and multiply 1.5 times 0.70. But I just wrote it out so you guys saw what I was talking about. And the last problem says, calculate the molarity of a 0.06 moles of NaHCO3 in a 1.5 liter solution. Okay, and they're asking us for molarity. So they're giving us the moles, they're giving us the liters, and they're asking us for molarity. Remember that molarity is big M, and it's moles over liters. So molarity is moles of solute divided by liters of solution. This problem is a very simple one. We're just going to plug in our values into the equation and solve. So moles is 0.060 moles of NaHCO3 and divided by liters of solution, which is 1.5 liters. I'm going to divide these two numbers to get 0.04 big M, so 0.04 molar NaCO3. Okay, when you're reading this, you're gonna say 0.04 molar. The molarity, you're gonna read it as molar NaHCO3. Okay, you're gonna read it as molar. And that's it. It's pretty easy. It's just you need to remember the molarity is moles over liters. It tells you how many moles of solute you have dissolved in order to make your solution. Okay, the higher this molarity, that means that the more concentrated your solution is. The lower the number, the more diluted your solution is. Next class, we're going to talk about diluting solutions, and you guys are going to see.